further geometrical properties. We've got 3 more. So the first one, quarter contact from a point. So we've talked about the quarter contact for ellipse, hyperbola. So I'm going to prove them for the ellipse today. You can prove them for the hyperbola, but I'm just going to focus on the ellipse. Right, so we talked about the quarter contact, the external point T, tangent to the ellipse, and it forms the quarter contact. If that external point is on the directrix, right, the quarter contact is a focal chord. Okay, if that external point is on the directrix, then the quarter contact will be a focal chord. In other words, the quarter contact goes through the focus. Okay. So, as the point T is on directrix, so it has so we've got point in the directrix, so the x value on the directrix, of course, A over E. And it doesn't matter which y value, okay, it'll always work. Right, so the quarter contact for your ellipse, so the first one we did. So x naught x over a squared plus y naught y over b squared is 1. Okay, so we covered that a while ago now. Right, so I'm going to substitute that point T in there, of course, so now I know what the x value is. So a over e times x all over a squared plus y naught y over b squared is 1. Okay, so just tidy it up a bit, so it'll be x over AE plus y naught y on b squared is 1. Once you multiply by the reciprocal, cancel, that's what you get. Okay, so the quarter contact must go through the focus for it to be a focal chord. Okay. What's the coordinates of the focus? AE, comma 0. We just need the positive one because that's what I'm basing it on, that particular foci. Right, so simply substitute that into your equation there. So AE over AE plus 0 is 1. Okay, so 1 equals 1. Okay, so the external points on the directrix, it will the quarter contact will go through the focus. It becomes the focal chord. The same with the hyperbola as well. Okay, so set up similar proof with your hyperbola, and you'll get the same sort of outcome. Right, number 2. Furthermore, okay, so again, if you pick the point, the external point on the it's not the same property, so if you pick the point D on the directrix, you draw a tangent to the ellipse at P, and then you join D with F and P with F, it'll always form a right angle. Okay, so you pick some point in the directrix, right, tangent at the point P, and then join the foci with D and P, it'll always form a right angle. So the tangent between the point of contact and the directrix will subtend a right angle on its corresponding focus. Okay, so what we really want to do is prove, we're required to prove the angle PSD is 90 degrees. Right, I'm going to use parametrics. So P, use A cos theta, B sine theta. In the tangent at P has the following equation. So X cos theta plus Y sine theta over B is 1. Okay, so yes, we did cover that during the relevant session. Alright, so taking the point D, I know the X value is A over E. Okay, so I'm doing a similar sort of setup so far. So I know at D, X is A over E, because there's a point on the directrix. So A cos theta over AE plus Y, do we make it Y naughts yet? No. Y sine theta over B is 1. Okay, so what we're really doing is we're finding the Y value at the point D. Okay, so we know the X value, we know the line it goes through, we're going to now get the Y, corresponding Y value. Alright, so just save a bit of time. Alright, so once you tidy that up, etc., you're going to get B, that's sort of E minus cos theta over E sine theta. Alright, so now we have the point T, so T has the coordinates A over E and B E minus cos theta over E sine theta. Okay, that's the coordinates of T. Alright, so we want to show that that's 90 degrees. So if I find the gradient of this, and I find the gradient of, if I find the gradient of DS, and I find the gradient of PS, and show that it equals -1, then it must be a right angle. Okay, so that's where I'm going now. So the gradient of PS right, so we had the Y value as B sine theta. So Y2 take away Y1 over X2 take away X1. So the Y value P is B sine theta. The Y value of S is 0. It's the foci. Over A sine theta. Take away the X value of S. AE. Alright, so B sine theta over A outside of sine theta take away E. That will help me later. Right, the gradient of, so I've done PS, so now I need SD. Again, I've used D's. Okay, there's T, that's where it came from the formula. Sorry. Right, so now I know the point T, and already know what S is. Alright, so B, outside of E cos E take away. Okay, so just substituting into your gradient formula. 1 minus e squared outside of a sine theta. Okay, that's the minus sign between 1 and the e squared. Okay, so that 1 minus e squared is very familiar, isn't it? Okay, what's it from? So what else do I need there to have b squared? Well, b squared is equal to a squared outside of 1 minus e squared, isn't it? Yeah, so I've only got a. Alright, so what I'm going to do is I'm going to write it like that. A squared, 1 minus e squared, over a times sine theta. Right, so I've got to square a because b squared is equal to a squared outside of 1 minus e squared. And that relates your eccentricity with a's and b's for your ellipse. So b, e minus cos theta over b squared over a sine theta. Okay, so I'm observing what I've got on this side as well. If I've got the reciprocal and the opposite sign, I then can show that it equals -1 when I multiply them. Right, it's going to equal a outside of e minus cos theta over b sine theta. Oh, this should be cos theta. So, alright, and then can we see that if we multiply these two fractions, because this is e take away cos theta, this is cos theta take away e, alright, you're going to get -1 when I multiply them together. Okay, so therefore, so now I've set it up, therefore MPF times st is going to be -1. Now that I've set up the fractions, I can very clearly see it's going to be -1. So that means angle PST is going to be 90 degrees. Okay. Questions on that one? Oh, did have a back page. Alright, so number 3, reflection property. You've probably heard about this in your physics already. No? So a tangent at the point P on an ellipse will be equally inclined to the focal chords through P. Okay, so what we're saying, in other words, the normal through the point P, which is here, okay, will bisect the angle S prime PS. That means this angle here equals that angle there. Okay, so that's what we're saying about the reflection property. Right, so you see on the diagram I have extended the tangent to the points on the directrix on the respective sides, and I've labelled them the variables as appropriate. Okay, so of course I've got a point P here, we really want it up there to be able to look at this property. Right, so what I'm going to do, a couple of things. I'm going to put the horizontal right, so I'm going to call it N prime, and I'm also going to drop the vertical. Through the point P. Right, so looking at your mathematics, PD over PD prime. Okay, so what I've already done here is I made this parallel to the y-axis and the directrix, of course. Because I'm going to look at the ratio of my intercepts and parallel lines. So PD, the ratio of PD to PD prime got to equal the same ratio as Pn to Pn prime. This is my ratio of parallel lines that we learnt in mathematics. Okay, ratio of intercepts of parallel lines. Right, so we're just going to swap them around. So PD over Pn is going to be equal to PD prime over Pn prime, just getting the primes on one side and the non-primes on the other. Okay, so PS is equal to P, so E, PD. N, we're going to make it so. EPN. So remember, the centricity is the distance from the point P to the focus and the perpendicular up to the directrix. Okay, so that's my perpendicular. That's why I had to include that. And my PS prime is going to be E multiplied by P N prime for the other side. My definition of the ellipse. Right, so I'm going to replace Pn and Pn prime. So PD. So Pn is going to be PS over E. And my Pn prime is going to equal my PS prime over E. Okay, so we've got fractions on the bottom again, however, they will cancel because they're the same constant value on both sides, on the same spot, which fraction, so they'll cancel. So we have now PD over PS is equal to PD prime over PS prime. Right, angle PSD is equal to angle P S prime D prime, okay, which is 90 degrees. This was proven in property 2. So PSD, okay, if you pick the point on the directrix, drop it to tangent and do the right angle here. Okay, so that's what we did the last proof, and the same with here. So P S prime to D prime is also will be the right angle from the last property. Okay, now the secant. So cos is adjacent over hypotenuse. Okay, the secant. Okay, of angle SPD, so SPD, so that angle there, because we've got the right angle triangle, I'm now going to use trig, because I've got the ratio of PD and PF. Right? So PD is the hypotenuse. PF is the adjacent side. Okay, so we need the ratio of the hypotenuse to the adjacent side. Okay, so cos is adjacent over hypotenuse, but we need the reciprocal. So we have the secant of the angle SPD. And again, PD prime, PS prime. So PD prime, which is of course the hypotenuse of that triangle, and the angle, this angle here, will make this one the adjacent. Okay, over PS prime. Sec of angle, let's go back one step. So sec of angle SPD is PD over PF. Okay, which is that part of the fraction. And sec of angle S prime PD prime, okay, is going to be PD prime over PS prime. Okay, and because they're both the secant, therefore, angle SPD must equal angle S prime PD prime. Because we've taken the secant of both of them. Okay, so what we've just proved is those two dot angles there are equal through any point P with the tangent, not the n prime line. Okay, so if I move that point P around, I've got the foci joined up to the point P, okay, and I've got my directrices from the tangent, that intersection point. That means those two angles will be equal, and that's the reflection property. Okay? And here we choose property. But in a recent HSC Extension 2 exam, needed some knowledge of that to be able to do a question. Okay, no, you did not have to prove it, but you had to know about the reflection property to know that those two angles were equal. Okay, so there is a recent HSC exam that has asked that, hence why I am showing you in a bit more detail so you remember it, hopefully. Right.